revolutionary account of quantum theory. And on Friday, Nick Huggett, who is a well-known philosopher of physics, will be talking about the physics of memory. Don't ask me what that will be about. You'll find out if you come to the center on Friday in a week. Also, for those of you who might be interested, I want to remind you. Watch the mic. Yeah. So on. All right. In 2 weeks from now at the center on April from the 5th to the 7th, the center is organizing a conference on science and values. If you're interested in coming to that conference, please go to our website and register for the conference. It's useful for us to have a head count so that to order coffee and other things. Today, it's my great pleasure to introduce our 5th speaker in the annual lecture series. Our speaker today will be Nicole Halpern, who is a physicist at NIPS, the National Institute of Standards and Technology. She's also a research fellow at QUICS, as a Joint Center for Quantum Information and Computing Science. She's affiliated with the Department of Physics at the University of Maryland, and she is the PI of the Quantum Steampunk Laboratory, which has a really good website. So I actually highly recommend you have a quick look at her website if you haven't done it. She's the author of Quantum Steampunk, The Physics of Yesterday's Tomorrow, great title, in 2022 with Hopkins University Press. Quantum Steampunk won the Prose Award from the Association of American Publishers. She has recently won the 2024 Hermann Weyl Prize for her contribution to quantum thermodynamics. From her website, I'm not a philosopher of physics, I'm a philosopher of neuroscience and cognitive science, so I have to trust her. But from her website, her work envisions thermodynamics using the mathematical and conceptual toolkit of quantum information theory. Thank you for accepting our invitation. It's a real pleasure and honor to have you with us today. And the floor is yours.
Thank you very much for the kind introduction, and many thanks for the invitation to be here. Very excited to be with you today. But since this talk is about thermodynamics, I'll give a brief reminder what thermodynamics is. You probably know, I'm pretty sure you know, just sometimes when I talk to physicists and I ask them, what is thermodynamics? Nobody in the room can define it for me. Even when I am talking to physicists who say they specialize in thermodynamic phenomena, you are probably much better with definitions, but just as a quick review, thermodynamics is the study of energy, broadly, the forms energy can be in and the transformations amongst those forms. It was inspired by the Industrial Revolution. For the first time, steam engines were powering factories. Naturally, people wanted to know how efficiently they could operate. So they gave this theory an operational perspective, one might say, but the technological questions led to fundamental questions, such as, why does time appear to flow in just one direction? And also inspired some fun steampunk works about the nature of time. So I'm going to assume that, at least to most people, time appears to flow in just one direction. So why does it? Often when people put together answers, they will refer back to the second law of thermodynamics. One of people's favorite formulations of the second law, more or less, is every closed isolated system's entropy just increases or remains constant, with some caveats that are less frequently mentioned. For instance, the second law of thermodynamics was inspired by large classical systems, such as steam engines, because those were transformative technologies of that day. Today's transformative technologies include quantum devices, which look very, very different. This is part of the motivation for one of my fields, quantum thermodynamics. What do we do in quantum thermodynamics? Well, in parts, we go back to the laws of thermodynamics and see explicitly why they should apply to small and quantum systems, even things that are entangling with each other. We do other things in quantum thermodynamics too, just this is the goal that I see as most relevant to this talk. In the kind of recent formulation of quantum thermodynamics that has experienced a lot of growth recently. We rely a lot on the toolkit of quantum information theory, which can be cast as the understanding of quantum systems through how they store and manipulate information. I view this as a useful mathematical, conceptual, and experimental toolkit. If you're interested in more information about the field of quantum thermodynamics, I can point to these two reviews. They provide a nice introduction to this more recent quantum information theoretic formulation of quantum thermodynamics. The field has been moving very quickly, and these papers originally came out in 2015, so lots has happened since then, but they provide great foundations. And this book provides background information, some of the main results, some of the history, and is in the style of a conversation we might have over lunch if we happen not to have any napkins to write equations on. Given that there is this field of quantum thermodynamics, surely it has said something about the second law, because it's tough to talk about thermodynamics without confronting the second law at some point. So what have we learned about the second law from quantum thermodynamics? So here are the takeaways of the talk in case you fall asleep soon. First, we can derive from quantum theory or non-equilibrium statistical mechanics more refined variations on the second law that might be more precise or more detailed. I'm not aware of ways of using quantum phenomena as resources for breaking the second law. That is sensible modern formulations of the second law. There was a hope that quantum engines could break the second law. Again, there could be something that I'm just missing, but I'm not familiar with breakings of the second law due to quantum resources. But quantum phenomena provide new sorts of resources for kind of bending around the second law. So appearing naively to break the second law, but actually either violating some assumptions that are necessary for it, or subtly really being consistent with it. And in this sense, I think we can use thermodynamics to gain new insights into the difference between the classical world and the quantum world. I was just talking about how we're using quantum information theory in order to update thermodynamics, but we can also go the other way. I have to start with a little bit of background about the second law of thermodynamics if I'm going to talk about variations on it. Of course, there are many formulations of the second law. Most of them I'm not going to talk about because they're not the most relevant to the new results that I'd like to present. Again, one of the favorites, maybe world favorite formulations is based on entropy. There are even multiple versions of this formulation of the second law. I'm going to present one that I happen to find intuitive, kind of following Boltzmann in a sense. A few weeks ago, and also today at lunch, I was warned that there's a giant war between Gibbsian people and Boltzmannian people. I'm not participating in that debate. This is not about that debate. This is just a view I happen to find intuitive, and some other people do too. If you don't find it intuitive, fine. That's okay. The results I'm going to present, the main point of this talk, don't actually rely on this background. I just want to give everyone a reminder of what the second law smells like. Right. Let's start with entropy. It's useful to think about our favorite thermodynamic system, a classical gas in a box. It can be in some macro state specified by large-scale properties, such as the total number of particles and the temperature. Our system will also be in some microstate specified by a much longer list of all the particles' positions, their momenta, and maybe other characteristics like angular momentum, depending on what sorts of particles we have. A system can be in equilibrium. In equilibrium, large-scale properties remain approximately constant over time, and there's no net flow of anything such as energy or particles into or out of our system. One macrostate will be consistent with many different microstates. I'll call the number of consistent microstates omega. But suppose we know the macrostates. How ignorant are we about the microstates? I am talking about ignorance. I am talking about knowledge. Again, if you don't like that language, it's okay. What I'm going to talk about, what I'm really here to present, doesn't rely on this language. But we tend to assume that all of the possible microstates are equally probable. I'm not going to justify this assumption because that would require a whole other lecture. But the probability of any given microstate J will be 1 over the total number of microstates. So suppose that we learn which microstate the system is in, how much information do we learn, or how surprised are we? That amount is quantified by a quantity creatively named the surprise, the negative of a log of the probability that this microstate had. By the way, I'm going to be using base E logarithms because those are very useful in thermodynamics. It's very easy to see that in a simple case, this formula makes sense. Suppose that the microstate is predetermined. Only one of the microstates has a non-zero probability. That probability is 1. The negative of the log of 1 is 0. So it seems that we're not surprised at all. We obtain no information. And indeed, if the microstate was predetermined, we already knew what it was. So when we were told the microstate, we didn't receive any new information. So at least in this simple case, the formula checks out. And a more complete motivation for the surprisal is in chapter 1 of this. But we're usually not interested in any one particular microstates. Suppose we want to consider an average over the microstates. So we average with probability weight Pj over our surprisal. So for each of the Pj's, we substitute in from our earlier formula for the probability. So the summand becomes independent of J. And we can just multiply the summand by the number of terms, which is omega. We get a number of terms canceling with a probability. We can simplify this using a log law. So our average surprisal is the log of the total number of possible microstates. This is an information theoretic entropy. That's okay, but we said that thermodynamics is the study of energy. So how do we get energy in here? We can just take our information theoretic entropy if we want and stick an energetic number in front of it. Sometimes this is a good idea, sometimes this is not a good idea. I'm not saying that it is generally always a good idea, but it's what I'm going to do here. And a convenient energetic factor in thermodynamics is Boltzmann's constant of nature, 1.38 times 10 to the negative 23rd joules. At this point, I'm contractually obliged to show you a photo of Boltzmann's grave in Vienna. Yours in all these textbooks and talks and so on. But usually people don't tell you that he wasn't actually buried here when he died. But he was buried elsewhere. And then physicists got together and petitioned the government of Vienna to create this in his honor. At least that was what I was told by his, I think, great-great-grandson. But later members of his family were buried there. And indeed, here is the Boltzmann entropy formula. Okay, so we've reminded ourselves of what an entropy smells like. What does it do in the second law of thermodynamics? We'll have in mind a system in some equilibrium macrostate, some classical system. For instance, a gas whose particles are all clumped together in one corner of a box. We'll have in mind another possible equilibrium macrostate, such as a macrostate in which the particles are spread across the box. And we'll ask, under what condition can one macrostate transform into the other spontaneously? The transformation can happen spontaneously if and only if the entropy increases monotonically. And moreover, watching the gas expand across the box gives us the impression that time flows. There are caveats. We said that both macrostates are equilibrium macrostates. We said our favorite system that we're thinking about is a classical gas, so that the entropy is well defined to the extent that people can even agree about it. Also, the system should be very, very large. Physicists like to think about the thermodynamic limit in which the total number of particles and the total volume diverge while their ratio remains constant. How come Well, if the system is finite size, then the initial macrostate will probably recur because the space of possible configurations is finite, and effectively the gas is sampling them randomly. So probably at some point, that initial configuration will come up again. Just we would have to wait a really long time to observe it, most likely. And the larger the system, the longer we have to wait. We inherited these caveats from a time when people were thinking about steam engines. Thinking started to change pretty quickly. Extensions were proposed by the early 1900s. Brownian motion convinced people that they could not always ignore atomism. The materials consist of tiny particles that move randomly. Sometimes they move opposite the direction we expect. I'm going to talk about more extensions or variations on the second law. These come from quantum thermodynamics or non-equilibrium statistical mechanics. The first variation consists of what are sometimes called second laws, derived within the context of thermodynamic resource theories. I need to define that technical term, but as a quick synopsis, the takeaway of this part of the talk will be, we can use these so-called second laws to answer a question more general than the one that we just saw. Under what condition can this equilibrium classical macrostate transform into that one spontaneously? But the price we have to pay is mathematical. We can't just check one inequality, we have to check a whole family of inequalities. Now, what are these resource theories? Or first, what in general are resources? I think of resources as things that are scarce. They're valuable because they can be useful in performing operational tasks. For instance, money is a resource. As it is said, money does not grow on trees. It is scarce. And it's valuable because, for instance, we can use it to buy lab equipment, or if we're theorists or philosophers, use it to buy coffee. And what are resource theories? These are simple models developed in quantum information theory. We use them to model situations in which the systems we can access or the operations we can perform are restricted. For instance, in thermodynamics, we'll often think about an agent who's in some fixed temperature environment, so they can easily access only systems at thermal equilibrium relative to that temperature. And thermodynamics restricts everybody to obey the first law of thermodynamics, the conservation of energy. Some things are easily accessible, some operations are easily performable. In this simple model, we assume all these things are free, they cost nothing at all, and an agent can access as many of these systems as they like or perform as many of the operations as they like. Everything else is scarce and might be useful. We call it a resource. Using a resource theory, we ask what things can transform into what other things for free, what transformations cannot happen for free, and generally, what is possible and what is impossible. Here's a simple version of a thermodynamic resource theory. Thermodynamic resource theory can really be more general, but the complications are a little more difficult to explain. Using a resource theory, we track the transformations of some system of interest, let's call it S, and it's consists of at least one discrete degrees of freedom. For instance, a quantum two-level system that has two energy levels with energies E0 and E1. And this system might be realized as, say, the spin of an electron in a magnetic field. Something that isn't an example of this sort of system is the position degree of freedom of a particle in a continuous space. Continuous variable quantum theory can be really obnoxious, involve things like rigged Hilbert spaces. Discrete systems are a lot simpler. Experimentalists have great control over them. So a lot of people in quantum information like to focus on them, although the results may be extended. Our system of interest will be in some quantum state that I'll often represent with rho. I'm not talking just about wave functions. I regard a wave function as a particular representation of a quantum state of a particular sort, namely the quantum state of a system that isn't entangled with any other system or isn't a pure state. But a quantum state can be the state of a system that is entangled with some external system. Technically, when I write rho, I mean, I'm referring to a positive semi-definite trace one linear operator, but the technicalities won't concern us here. Our system is in some environments, which in our model is in thermal equilibrium at some fixed temperature T. And here's what can happen for free. Every free operation consists of up to 3 steps. First, a piece of the environment, let's call it E, can come over to our system of interest. Then the system and that piece of the environment can interact in any fashion that conserves their total energy or is consistent with the first law of thermodynamics. Finally, that piece of the environment can go away again. That's our resource theory, our framework, our model. What can we derive from it and quantum theory? These second laws of thermodynamic resource theories can answer the following question. Suppose that we have a quantum state rho, and we have in mind a quantum state sigma. Can rho transform into sigma for free, or can it not? This question is more general than the second law question that we talked about earlier. Neither rho nor sigma has to be in equilibrium states. Our system of interest, S, can be quantum, or it can be quasi-classical if you don't want for either of the states to have coherences relative to the energy eigenbasis, that's fine. So quasi-classical and quantum systems are governed by this framework. And also our system of interest S doesn't have to be extremely large. It can consist of a 2-level system if we want. The price we have to pay for this generality is the requirement that we need to check a whole family of inequalities. We can't just check, does this one entropic function increase monotonically? In fact, for answering at least part of this question, we have to check 2 different subfamilies of inequalities. One of the subfamilies governs probabilities. But suppose that we have our state rho, and we want to measure it relative, or we want to measure its energy. We'll get one of probably multiple possible outcomes, and each possible outcome has some probability. We can tell the same story about sigma. So how those probabilities transform is governed by the first subfamily of inequalities. And the second subfamily governs the coherences, so wave-like properties of the states. More technically, if we have our quantum state rho, we can represent it as a matrix relative to the energy eigenbasis, and the off-diagonal elements of the matrix are governed by this subfamily of inequalities. The math behind these second laws, I think, is kind of fun. It's majorization within probability theory. It was actually developed during the early 1900s by economists who wanted to quantify how unevenly wealth is distributed across a population. So there are things in majorization theory called Robin Hood transfers that model the stealing of money from the wealthy and the gifting of that wealth to the poor. And Robin Hood transfers actually do show up in resource theories, as you can see from a technical perspective in this review, and also less technically in the book. So these are some of the early papers and landmark papers in the study, the development of these kind of second laws, and more prose-focused explanation is in chapter 11 of this book. So much for variation number 1 on the second law. The second variation on the second law involves the use of correlations, including entanglements, to move heats, even on average, from a colder system to a hotter system. By entanglements, I mean a relationship that quantum particles can share and classical particles can't, that can lead to correlations and measurement outcomes that are stronger than any we can prepare using just classical systems. And of course, the entanglement was also the subject of the Nobel Prize in Physics in 2022. The results I'm going to present is in this, what I think of as a cute little paper by David Jennings and Terry Rudolph. The relevant formulation of the second law is the Clausius version from our friend Rudolf Clausius, who helped found thermodynamics. Clausius said that heat can never pass from a colder body to a warmer body without some other change connected therewith occurring at the same time. So if we go into our kitchen and, oh, right. So I should mention, we like to add in the phrase on average because, again, we know about Brownian motion. We know materials consist of tiny particles that jiggle randomly, and sometimes they go oppositely we expect. So if we go into our fridge or into our kitchen and we open up the fridge, of course, on average, heat is going to flow into the fridge. A little bit of heat will flow outward, but mostly heat will flow inward. And therefore, in order to keep our fridge cold, we have to have it plugged in. We have to spend thermodynamic work. This expenditure of work is this some other change in the Clausius formulation of the second law. More abstractly, we can have a system at a higher temperature T hots and a system at a lower temperature Tc, such that they can exchange energy. Again, mostly heat is going to flow from the hotter to the colder system, although a little can flow in the opposite direction. Moreover, watching heat flow mostly into the colder system gives us the sense that time is passing. Well, now let's focus on this possibility of some other change. And we'll come to think about some other change that is maybe not obvious as being able to be used as another change. And in order to get to that point, I'm going to start off on what looks like a detour. The question, what does it mean for a classical system to have a temperature? Well, suppose that we have a system, we measure its energy. The outcome is going to be some random variable, particularly if the system is well described by statistical mechanics. And suppose that the probability of obtaining the amount E is proportional to an exponential that has a negative sign, depends on the energy, depends on Boltzmann's constant, and has some other real number here. In this case, we'll say the system is at thermal equilibrium, and it has a temperature equal to that real number. Now, what does it mean for a quantum system to have a temperature? Well, the system has to satisfy the same condition regarding measurements and probabilities, although it also has to satisfy an extra condition on its coherences. So if you take our system, it's in some quantum state, we represent that as a matrix relative to the energy eigenbasis. All of the off-diagonal elements of our matrix have to be 0. So suppose we have a hot system and a cold system. We measure the energy of each. We'll obtain some random variables, E hot and E cold. Now, random variables, of course, such as E hot and E cold, have the possibility of sharing correlations. We can start to think about correlations by first not thinking about correlations and recalling what it's like to have two independent random variables, such as two coins that we flip independently. But let's call our random variables C1 and C2. Each has the possible values heads and tails. Suppose that each of our coins is fair. So the probability that coin 1 lands heads up is 1/2. The probability that coin 1 lands tails up is also 1/2. And analogous statements are true of coin 2. We can easily calculate joint probabilities. What's the probability that coin 1 and coin 2 land heads up? That joint probability is just the product of the two individual probabilities. Each of those is 1/2. And so our joint probability is 1/4. We can go through this rather boring exercise for each of the other possible joint outcomes. In each case, we'll get 1/4. So we have a nice, sensible joint probability distribution. Now suppose that our random variables are correlated. I don't know how to draw or really conceive of coins that are correlated, so I'll just put tildes over my coins and also tildes over my random variables. So tilde C1 can have value heads and tails, so can tilde C2. And suppose that if we look at any coin individually or any of these random variables individually, it'll look like a fair coin. Again, the probability of heads is 1/2, the probability of tails is 1/2 for both coins. But we can put together a different joint probability distribution. It can be the case that the probability of 2 heads is 1/2, and the probability of 2 tails is 1/2. By normalization, both the other joint probabilities have to vanish. This joint probability distribution is consistent with our individual probabilities, but it encodes correlations. Because if we know the outcome of one coin flip, we automatically know the outcome of the other coin flip. Because if we see heads, we'll know about another heads. If we see tails, we'll know about another tails. So if there are correlations and we know about just one variable, we automatically have an extra resource. We automatically have information about the other variable. We can use an informational resource, which might be encoded in a quantum state, in order to perform our task of pushing heat in the quote-unquote wrong direction. Before we get to the operations, we should think about quantifying information. We tend to like to quantify information about quantum states, in part using the von Neumann entropy. The von Neumann entropy of a state rho is the negative of the trace of the state times the log of the state. This formula very much parallels the formula for the Shannon entropy. And this, fairly straightforwardly, is interpreted as our average uncertainty about the outcome of a measurement of the state. Suppose that we measure rho in its eigenbasis. Still, in most cases, we won't know the outcome. We only know possible outcomes and probabilities thereof. So we still have some uncertainty about the outcome. Again, I am now talking about information in the context of thermodynamics. I'm not going to say that it's always useful to take an informational entropy and equate it to something in thermodynamics, and the two types of entropies are equal to each other. I'm not saying that. As a matter of fact, when I saw this von Neumann entropy in this paper, I was quite skeptical about whether it would be used properly. Here's what Jennings and Rudolph say about their use of the von Neumann entropy. The identification of the information theoretic quantity with a thermodynamic variable has generated a long history of debate. I think they could have cited far more than 2 papers. However, we do not add to this debate here, since the operational and mathematical correctness of our analysis holds independent of such interpretation issues. So I was very skeptical, but I ended up agreeing with them. I find their proof very straightforward. It's some algebra and the identification of expectation values, which I don't find very controversial. We can use the von Neumann entropy to define another entropic quantity, the mutual information. The mutual information between a state rho hot and a state rho cold is the von Neumann entropy of rho hot plus the von Neumann entropy of rho cold minus the von Neumann entropy of the joint state. And an interpretation of the mutual information is as the amount of information that one system has about the other and vice versa. The Bible of Quantum Information and Computation is a textbook by Nielsen and Schwang, and they illustrate the significances of entropic quantities such as the mutual information by showing Venn diagrams. They don't actually put words to their Venn diagrams. I'm going to attempt to put words to their Venn diagrams, but because I think that at least the Venn diagrams look kind of intuitive and helpful. So suppose that we know the form of rho hot. Still, we have some uncertainty about our system because, again, if we measure our system, in most cases, we can't predict the outcome. We just know about possible outcomes and their probabilities. So how uncertain are we about our system? Even if we know the form of rho h, we can quantify that with the von Neumann entropy of rho h, at least on average, and that's represented by this blob, our uncertainty. We can tell a similar story about rho cold, and our uncertainty about that is represented by this blob. Now, we can also tell the story about the joint states of rho hot cold. And that uncertainty, well, on Keynote, I didn't know how to draw a blob that was exactly the outline of these two, so the green box is the best you're going to get. Now, suppose that we take the uncertainty about rho h, we add the uncertainty about rho cold in accordance with our formula here, and we subtract the uncertainty about the joint state. What we're left with is this purple intersection, because we added it on once in the red blob, we added it on again in the blue blob, and we subtracted it off only once in the green blob. So the purple is what we're left with. Illustratively, it is in both the red and the blue, and so it represents the mutual information between the hot state and the cold state. Okay, let's use that mutual information. So we can use an informational resource, according to Jennings and Rudolph, to push heats from a colder system to a hotter system, even on average. So again, we have our abstract hot system and cold system. I'm going to, in a cartoon fashion, represent the correlations that they start off with these fuzzy green lines. This whole thing is going to be a closed, isolated system. No work is performed on it. It doesn't couple to some other heat bath because we're just interested in the heat that's flowing between them. And so we don't want to complicate our picture with also energy that's coming in from outside. So we won't allow energy to come in from outside. Let's denote by QH, the average amount of heat that flows into the hot system. When I say average, I mean in the sense of expectation value. An expectation value is inherently an average over many trials. Right. Jennings and Rudolph proved this generalized second law. States that the average heats flowing into the hotter system times this temperature-dependent factor is at least the change in the mutual information between the hot and cold systems during the heat flow process. We can start to get a sense of what this generalized second law is like by recovering a statement that we should be able to agree on, probably, in a special case. So let's see how we can recover a more conventional looking second law statement. Suppose that the systems start uncorrelated. When we usually think about statistical mechanics and thermodynamics and the second law, we're usually thinking about hot systems and cold systems that have never had anything to do with each other before. They're independent. So our initial mutual information vanishes. So what can the change in the mutual information do? The mutual information can only grow or remain constant. So the right-hand side of our inequality is positive or constant, or zero, excuse me. What about this temperature-dependent factor? Well, TH is high, it's large, so this fraction is small. This fraction is bigger, and so this whole thing is negative. We have a negative quantity on this side times this QH. They have to multiply by something up to something positive, or zero. So the only option for QH is for it to be negative, or zero. What does that mean physically? Well, we said QH is the average heat flowing into the hot system. So on average, negative heat flows into the hot system, or no heat. Or in other words, on average, positive heat flows out of the hot system, or no heat, which is what we expect by the ordinary second law of thermodynamics and everyday experience and so on. So from the generalized second law, we do obtain a statement that we expect. But our systems can instead begin correlated. In this case, the mutual information doesn't have to grow. The change in the mutual information can be negative. And so we might think of the correlations as being used up during the heat flow process. And mathematically, the possibility that this is negative allows for this to be negative. So we can use up the correlations to push heat into the hotter system. Sorry, I might have said negative here when I meant positive, but I think you know what I mean, that there is a possibility for heat to flow even on average into the hotter system. Entanglement, we said, allows for correlations that are stronger than any we can achieve classically. So you might expect that if that entanglement can allow for especially large heat flows in the quote-unquote wrong direction. And indeed, if enough heat flows in this so-called wrong direction on average, then you can conclude that the initial state must have been entangled. In other words, we can use anomalous heat flow as a thermodynamic witness for entanglement. So we can use thermodynamics to inform us about a particularly quantum phenomenon. So much for our second variation on the second law. So the third variation consists of fluctuation theorems or fluctuation relations. These were originally derived in non-equilibrium statistical mechanics and then were appropriated by some of us in quantum thermodynamics. Key properties of a fluctuation relation include how it's an equality, even far from equilibrium. The ordinary second law is generally an inequality. So if a system just remains in equilibrium, then its entropy is not going to change. The second law is going to be an equality, but equilibrium is very special and also very boring. So it's nice to have rigorous statements that are equalities, even far from equilibrium. Second, fluctuation relations were first proved for classical systems. They were later proved for quantum systems. And fluctuation relations also imply something that's often called the second law, but it's really an implication of the first and second laws. I'll show you shortly. But we can also use fluctuation relations to gain detailed predictions or precise predictions even about single trials, not just averages. I'll illustrate fluctuation relations with an example that was realized experimentally. It's a classical example, but I think it presents a really nice story. So consider a DNA hairpin. This is a single strand of DNA. It has a loop at the top, and it has these two handles that come outward. If this DNA is in some aqueous fluid at room temperature, then the hairpin is going to be classical. And suppose that the hairpin is in thermal equilibrium at a temperature T around room temperature. According to our definition of temperature, if we were to measure the energy of this hairpin, we would find that the energy is distributed according to this exponential with our partition function here. Or here, mu I is the density of states relative to this relaxed, floating in the aqueous solution configuration of the DNA hairpin. Since our DNA hairpin is in thermal equilibrium, we can ascribe to it an equilibrium Helmholtz free energy. The free energy often quantifies how much work a system can perform. And it equals the negative of Boltzmann's constant times the temperature times the log of the partition function. I'll call this F sub I, or initial F. We can define the following forward process. We can put a tiny styrofoam bead at the end of each handle. We can trap one bead using a laser beam or optical tweezers, which were responsible for another recent Nobel Prize. So this is going to stay put. And we can use a micropipette to grab onto this bead and pull it in this direction. We can pull it at any speed we want. If we pull it at a finite speed, the system is going to pop out of equilibrium. We can pull at any speed, but let's pull it through some fixed distance that we decide beforehand. How much work do we have to expend? To stretch something, we have to expend work. The amount of work is a random variable. It changes from trial to trial because in one trial, some water molecule might kick the DNA strand in this direction over here. And in some other trial, a water molecule might kick the DNA strand from this direction over here. And there's even more randomness in the problem. So work is a random variable. But suppose we perform lots of identical experiments. And in each experiment, we measure the work that we had to spend. From these measurements, we can infer a probability distribution, P forward, that tells us what is the probability that in the next trial, we'll have to spend an amount W of work. Now, we've stretched our DNA strand, and suppose we let it hang around forever in this stretched configuration. Eventually, the DNA strand will rethermalize. We don't actually have to do this in the experiment, and the experimentalists who undertook this experiment did not let the strand sit around forever, obviously, but we can imagine that they could do this. And in this case, after this rethermalization process, the DNA strand would have a different amount of free energy that would depend on its new stretched strand partition function. Now let's define as delta F this final imaginary free energy minus the actual initial free energy. We can use the first and second laws to conclude that on average, the amount of work that we have to spend in a trial is at least the change in these free energies. And an equality is reached when the process is quasi-static, so slow that the system always remains in equilibrium. We can also define a reverse process. We can start off with the strand in its stretched configuration in thermal equilibrium, and then we can bring the pipette toward the tweezer and allow the DNA strand to recollapse. In this case, we'll recover work. How much work? Also, this is a random variable, but if we perform a bunch of trials, we can infer another probability distribution. So P reverse of negative W is the probability of probability density that in the next trial, the amount of work we'll recover from the reverse process is W. This story obeys something called Crookes theorem, a very famous example of a fluctuation relation. The placement of the apostrophe is very important. Gavin Crookes is not a criminal. And as a matter of fact, one of my favorite intellectual so-called possessions is an email I received from Gavin Crookes. I wrote my first paper on fluctuation relations during the first year of my PhD. And so shortly after that year ended, I received this email from Gavin saying, "May I particularly commend you for putting the apostrophes in the right places." Well, he also expressed some interest in the paper, so I didn't feel so bad. Punctuation matters. The Crookes theorem is this statement. The probability that we'll get an amount W of work, or sorry, the probability we'll have to spend an amount W of work on a forward trial over the probability that we will recover an amount W of work in a reverse trial is this exponential. Now, the exponential depends on the W that is in question, this random variable. Also, this free energy difference and our favorite energy dimensions factor. How do we interpret this? Means we're exponentially more likely to lose an amount W of work than to gain it. Suppose W is really large. This exponential is really, really, really large. So the probability that we'll have to spend a huge amount of work is really, really, really large compared to the probability that we will gain a large amount of work. And so this equation is very much consistent with the popular synopsis of the second law: you can't win. Also, via 3 steps, you can derive from Crookes' theorem this thing that people often call the second law, or implication of the first and second laws, which is a statement about an average. But Crookes' theorem also tells us about every single trial through these probabilities, which tell us about single trials. In addition, we can use Crookes' theorem to upper bound our probability of getting away with less work than you would expect during a forward trial, or conversely, gaining more work than you would expect in a reverse trial. So we expect, because of our average statement here, that in a forward trial, we will tend to have to spend at least delta F of work, and we'll probably have to spend more. But because systems are made of particles that move randomly, occasionally we'll get away with spending less work. Just the probability of that is very small. And Crookes' theorem upper bounds that probability. Question?
I have a question. My question is, are we allowed to ask questions?
Are they allowed to ask questions?
Let's wait for the end. Also, we're almost done, so let's wait for the end.
Okay, and I am almost finished. So Crookes' theorem is in the paper up there. Jarzynski's equality is another very famous fluctuation theorem. It's actually technically an implication of Crookes' theorem, but was discovered first. And I think chapter 9 is entirely about fluctuation theorems in this book. So we've talked about a couple of ways of, in my words, bending around the second law. We said that we can push heat in a direction that looks like the wrong direction but we have to pay a price. It's just kind of a surprising price that you might not expect naively. We consume correlations. We can spend entanglement to push heat in the quote unquote wrong direction. We also said that in the context of fluctuation theorems, we can sometimes get away with spending less work than we expect, just with low probability, of course. There are even other ways of bending around the second law. One example involves an engine that is given access to a reservoir that's in a squeeze state. So a conventional heat engine will interact with a hot reservoir and a cold reservoir. We can define engine cycles for quantum systems that are analogous to the engine cycles for classical systems. And something that has been proposed and also experimentally tested is an engine that is given access to a fairly ordinary thermal reservoir and a reservoir that in some senses looks thermal, but is in the squeeze state. So a quantum system is in a squeeze state if it has 2 conjugate properties, kind of analogous to position and momentum, such that the uncertainty in one of the positions is very, very, very small, just at the cost, of course, of a very, very large uncertainty in the other property. And there are even more examples. So, what have we seen? I've proposed that quantum thermodynamics and non-equilibrium statistical mechanics offer generalizations and refinements of the second law. We saw what are sometimes called second laws defined in the context of resource theories. We saw that we can use correlations, including quantum ones, to push heat even on average from a colder system to a hotter system. And we saw fluctuation relations, which give us more detailed information about single trials. So, according to my perspective, the spirit of the second law more or less seems to live, even though we have needed to update the wording. But something that I find very interesting is that quantum physics offers us new sorts of resources for bending around the second law. And so we can learn from thermodynamics about quantum foundations, not only use quantum theory to update thermodynamics, but also use thermodynamics to understand better what quantum systems can do that classical systems can't, and where the divide lines between the quantum and classical worlds. Thank you.
Now we have plenty of time for questions, so please raise your hands and I will call on you. Yeah, please go ahead.
Hooke's theorem, I don't know what goes into proof of it, but it seems like the directionality of time is very important. Reverse time, definitions of retrue time flips. So either they assume it in the proof, or it's a proof that time is direction. Seems like there's some dramatic connection.
The proof, let's see. So I was using Crookes theorem about a decade ago, and I could have told you all the assumptions that go into it then, but for instance, microscopic reversibility goes into it. It was first derived with classical mechanics, probably a Markovian bath, and that's probably the direction of time. I wouldn't be surprised, though they weren't trying to come up with a proof that time flows or anything like that. So I think they probably wouldn't argue with you, and I think that if we just went through the paper, we could find the element that you're identifying. And I would guess it might be the Markovianity assumption.
David?
Well, just a comment on that, actually. I mean, at least the version of proof I know, I think the asymmetry is coming in because you assume the initial, either the initial system or the initial environment is exactly in the canonical, the microcanonical.
Oh, that's another one, yeah.
And then the end probability distribution given something maybe force rates that is.
Yeah, so each of the protocols, the forward protocol and the reverse protocol, starts with a system in equilibrium. You drive the system out of equilibrium, and then you can imagine that the system, if you let it sit for long enough, the system will eventually rethermalize.
Yes, please go ahead.
I don't know.
Yeah.
The mutual information, just thinking intuitively, you think that as time goes by, it has to increase. So just kind of we're communicating on. That again sounds like sort of an arrow of time stuff. But you had examples where you have an example in mind where it doesn't happen. So I guess it's a statement at some microscopic level, this doesn't have to happen.
That's
Go the other way.
the claim in the Jennings-Rudolph paper. So if we think about that simple setting in which we can recover the second law-like statements, then we start off with systems that are uncorrelated, and the intuition that you have in mind is exactly what we use. The mutual information starts off 0. It can only increase or remain constant. If the system starts off with certain correlations in it already, there exists an evolution. At least in certain cases, there exists an evolution. So in this quantum setting, there exists a unitary operation such that you can decrease the correlation in order to push heat in this quote unquote wrong direction. And at least in their paper, Jennings and Rudolph, as far as I could see, didn't present an example with this simple one hot, one cold system. Kind of unfortunately, they did present examples that were just multipartite and so more complicated, but they basically did find there are cases in which you can decrease the correlations to move heat in the kind of wrong direction. But I doubt it. So they derive a bound such that if you see average heat flow in the wrong direction that lies above the bound, you can conclude that the initial correlations were entanglement. But if you, because no classical correlations can exceed that bound, but if you see heat flow in the wrong direction that lies below the bound, then classical or quantum correlations might be the source.
David.
I'm interested to try to understand how much we get out here with specific quantum and how much is simply about microscopic systems. So one thought would be once we start doing the thermodynamics in full systems, firstly, we realise that there are richer result field questions than just how much energy we get out of average. We have fine grained best language distributions, measure language distributions. And secondly, we realise that if two systems are correlated, then the kind of effective phase-based volume they occupy is going to be less than the product of the effects phase-based volumes that they occupy separately, and so we can see it into a smaller space than we expect to be able to if the systems are uncorrelated. And thirdly, we'll learn from Brooks and Judzinski's that there's a much richer story to tell about fluctuation phenomena with just the inequalities. And then, of course, when we come to quantum mechanics, we'll realise that the actual specific form of each of those claims will need to be, we'll need to see whether it can be generalised, whether we can do the kind of correlation to impact movement, gives everything wrong and entropy, mutual information to its quantum version when it moves, and in general we find that is possible. Are there places where there's something qualitatively different in the quantum mechanics that isn't coming up simply in that and might be stopping?
Yeah, so two examples come to mind. It's the more dramatic one is in the context of fluctuation relations. This is actually a big problem to fluctuation relation theorists or quantum ones. We talked about, we formulated Crookes' theorem in terms of the work required to pull the strand or the work you can recover from pulling the strands. How do we define work? Well, sometimes we define work by saying, this is how much energy my system had. This is how much energy it has now. Energy came out. Whatever that comes out, whatever that came out that wasn't heat is work. But to know how much energy my system had originally, I had to have measured it. And now I have to measure it again. And all that is extremely disruptive. So a good way of formulating quantum fluctuation theorems has been debated since my first year as a grad student. Well, no, earlier, significantly earlier. So there's the Tosaki-Crookes theorem that involves something called a two-point measurement scheme. Measure the energy of your state initially, perform a unitary operation, don't let your system interact with the heat bath anymore, and then perform another measurement of the energy. So you know that you know how much the energy changed, and you know that the whole energy change came from work because no heat could have been leaving. But you destroyed all your correlation or all your coherences relative to the energy eigenbasis initially. That's very frustrating. So people have been coming up with alternative schemes. Some involve weak measurements that don't decohere the system too much. Some involve just single energy measurements, just they don't give us as much information. So I think that's a place where the quantum problem is qualitatively different from the classical one. Oh, yes. I was thinking I'm not sure if you'll find it satisfactory. So I mentioned that we have multiple subfamilies of inequalities as far as second laws go. So initially, people just studied a quasi-classical problem completely. They said, my rho will be representable by a matrix diagonal relative to the energy eigenbasis, also my sigma, and then derived these second laws for the probabilities on the diagonal. And then people started building in coherences and found a subfamily of second laws for the coherences, but those were only, I think, necessary and insufficient. And then a group of people got together and solved this problem completely by taking majorization theory and generalizing it to what they call matrix majorization. And by developing new math, they managed to solve the necessary and sufficient problem.
So we would diagonal, you had expected just to be a plain classical situation for diagonal.
Yeah, Could you maybe go back to slides where you were? Oh, yeah, this is it. Sorry, that was it. Yeah. So that second dot where you say we can sometimes spend less work than expected, but with low probability. So I'm trying to combine this sense of low probability with everything you said about like how we should interpret resource theories or like dealing with this with quantum thermodynamics as a resource theory. So like if you can only spend less work than expected with low probability, does that make it less of a resource? Like if does that question make sense?
But quantum thermodynamics is actually really like this question. And so we see certainty as a resource. And something that is done a lot is to quantify trade-offs. So some things that can be traded off can be how much work I have to spend and the probability, like how guaranteed am I to exceed my work budgets or not exceed my work budgets? For instance, you can imagine, and there are situations in which risk-taking agents will perform a riskier protocol that has a higher probability of costing them tons of work, just because sometimes they'll get away with spending almost no work, and they're willing to accept that risk. But a more risk-averse agent will perform something more, like you can think of it as kind of closer to the quasi-static protocol. The amount of work required is almost guaranteed, and just every single time they're going to have to spend probably about this amount of work, and they have almost no probability of getting away with zero work. So we can see the certainty of what we'll have to spend itself as a resource.
Yeah.
Thanks, Chair. I also had to think on this third variation you said. So maybe our question is, what's so different about quantum thermodynamics to the third variation? Because if you kind of take the statistical interpretation of the second law, I think there are cases where entropy that obviously automatically increase. Is the novelty here that you can actually bend a control in precise ways situations where you get violation, but this is the novelty with quantum thermodynamics.
Okay, so there seem maybe to be two strands to separate out here. One is, what do we get from, or how is the quantum thermodynamic version different from the classical thermodynamic version? We said that, so variation number 3 consists of resource theories. Resource theories have been proved for classical systems and for quantum systems. How the quantum version differs was my excessively long answer to David's question. That involved basically the problem of having to measure energy, things like that. And maybe the second or the other strand of your question is, what do we get from fluctuation theorems that we don't get from the conventional second law? So from the conventional second law plus the first law, we get this. It's the statement that on average, the work required to stretch the strand is at least the free energy difference. We can recover that from Crookes theorem, but we also get a lot more from Crookes theorem. So we get something that is consistent with the spirit of the second law, but the second law is not nearly this quantitative or detailed. And also, as you mentioned, the second law, since it's phrased as an average, the second law is consistent with, the second law allows for how we can sometimes get away with less work than expected. Just using Crookes theorem, we can upper bound the probability of getting away with less work than expected. So the second law, again, allows for, there is consistent with this probability, says nothing about the probability of that possibility, but we can quantify that probability using the fluctuation theorem.
Hi, so I'm interested in this characterization of thermodynamics as a resource theory. And what I think you're saying is that in quantum thermodynamic case, you have additional resources that you weren't expecting to have in the classical case. I'm wondering if there's cases in the opposite direction where in the quantum mechanical thermodynamic case, you've sort of lost a resource you thought you had in the classical case. Is that something that makes sense?
Well, if we regard the ability to define work straightforwardly as a resource, we do lose that in the quantum case.
Okay. just
Because,
definition.
for example, because of this measurement issue, I guess we can certainly say some things become irritating and problematic and troublesome in the quantum case, like the question of what are quantum heat and work, how do we define them? Those questions, what are quantum heat and work, are some of the biggest problems in quantum thermodynamics, and they do affect quantum versions of fluctuation theorems.
And so these would be resources?
So I, as someone who want to use definitions of quantum heat and work, regard the ability to formulate those definitions in a useful way as resources. I probably was being a little tongue-in-cheek. I would expect that what you can do with classical systems, you can do with quantum systems to within like measurement disturbance and uncertainty problems. Yeah, so decades ago, people were wondering, can we know that we can use classical systems in engine cycles to run heat engines. Can we possibly do the same thing with quantum systems? And by now, people have shown that there are quantum cycles. In some ways, they can outperform their classical counterparts. Oh, so some people have shown that, for instance, certain engine cycles, certain coherence is unhelpful and will actually hurt the performance of your engine. Although you could just decohere your engine, I guess, if you wanted to get rid of that problem. But maybe there's some situation in which measurement disturbance really deprives you of some classical resource. I haven't really thought about that.
That's kind of the situation I was imagining.
Mm-hmm.
Just like various ways you might conceive of Maxwell's demon that are different in case.
Oh, yeah. So, yeah, there's an example. So suppose that you have, suppose that we don't want to argue about Maxwell's demon. Suppose that I'm just trying to provide a simple answer to your question. And suppose you have a Maxwell demon that has a gas of 2 particles. So those particles could be distinguishable or bosonic or fermionic. Now, the fermionic engine performs worse in terms of average work performed per cycle. So it performs worse than the classical engine. On the other hand, the bosonic engine performs better than the classical engine. So I guess quantum resources, indistinguishability can hurt you or help you depending on which statistics you have.
Kevin.
Okay,
No, go ahead if you want.
this is more kind of self-serving question for me. So this is like the new area of information. If you maybe this is an invitation for you to really tell me if you think there are any very interesting conceptual problems here in quantum thermodynamics that you think that are suitable for graduate students.
About your writing dissertation.
Asking for a friend.
Well, the problem of how we should define quantum work and heat is a major one. So multiple definitions exist. I guess an overview is in chapter, I think 6 of my book. So that's just in case you want an introduction, but there's a lot more. So again, typically in order to define heat and work, we have to make measurements, or we have to have definitions that correspond to measurable properties, but measurements disturb our system. Suppose our system had coherences relative to the energy eigenbasis. It didn't have a well-defined energy. So if it didn't even used to have a well-defined energy at some point in time, how is the heat and work that it exchanges later well-defined? There are lots of different proposals. Some are more common than others. And they have their different pros and cons. I have seen a number of papers in which people say, I have the definitions of quantum work and heat. These are just the best, and they should always be used. I have a folder of such definitions. I personally am of the opinion, and I'm not the only person of this opinion, that different definitions are useful in different contexts. In different contexts, we have different equipment around. We poke our system in different ways. We have different measurement capabilities, and different definitions are suitable for these different contexts. I find this possibility interesting because so much of physics is portrayed as centered around unification. Particle physics is probably the most famous example. Everything has to come together, right? I like to think maybe quantum thermodynamics is a little richer so that there is no one set of definitions to rule them all. But maybe you will come up with those.
Okay, doesn't go into your folder.
Send me your thesis and I will consider it.
David.
The very last line of the book, we had this sort of teaser that thermodynamics might be called a foundation. You say more about what you haven't done?
Yes, sure. So I presented just, let's see, how many examples, maybe one example, we could say variation number 2 on the second law. We can use quantum correlations to push particularly large average amounts of heats in the wrong direction. And so we can use the observation of heats plus this proven bound in a witness for entanglements, which we like to think of as not classical. But there are other examples. I think this is a growing efforts and one that needs to continue. We can sometimes say if we observe some thermodynamic phenomenon, then we can conclude that the experiment we just performed is contextual. I particularly like that way of using thermodynamics to inform our understanding of quantum theory. So yeah, that's a growing effort.
Any more questions? 1, 2, 3. All right, so let's thank our speaker for coming back to join us for reception in the room, which is just right here with some delicious and not so delicious. Thank you very much. That was wonderful. Have a small gift. It's a tiny gift, but you can carry it in your plan. So it's an envelope. It's